Okay, this is from Copeland. This is example 3.2 on page 167. So we've done an ascending question. This equation that you need to commit to memory, it can also be used for descent, and it can calculate glide distances. Okay, so you might get a question where they're saying, for a given lift to drag ratio and a given altitude, how far can we glide? Well, they might say the airport's this distance away. So in this instance, it said we have a lift to drag ratio of 15 at an altitude of 1500 meters, and we have an engine failure. Will the pilot be able to glide to an airport 16 kilometers ahead? Okay, so dire situation, engine failure on approach. So will we make the airport? So you need to use that formula, theta equals thrust minus drag over lift. Okay, so we don't need to use weight. Now we do know that for this equation that our thrust is equal to 0. Okay, how do we know that? Because we've had an engine failure. So we know our formula is going to become theta equals minus d over L minus drag over lift. We know that our lift to drag is equal to 15, so it's equal to minus 1 over 15 in this instance. Okay, our answer is going to be in radians. Okay, so we grab our trusty scientific calculator and we go minus 1 minus 1 divided by 15. Okay, so we get a, I'm just going to make sure I've got the right answer. Yes, I do. We get an answer of minus 0.066666, etc., etc. Now remember how to change that. We can either multiply by 57.29 times 57.29, or we can go shift DRG and select 2 and go equals. And we end up with an angle of minus 3.8 degrees. Okay, so theta equals minus 3.8 degrees. So what does that mean? Now we need to draw a lovely little picture. Okay, so we've got our ground. We might try and make our ground horizontal. That's a very bad picture. Our ground that the aircraft is flying over. And we know our airport's 16 kilometers away. And we know our aircraft, which is flying up here, has had an engine failure, and it is at 1500 meters, and the angle going down, this angle here, is going to be the same as this angle here, okay, which is, like we said, 3.8 degrees. Okay, so we know, because if these two lines were parallel, we've got alternate angles. We've got an angle down here of 3.8. So we need to calculate this unknown distance here. Okay, let's call it D. Okay, let's call it DG. Okay, distance glide. So this is a simple trig problem. We have the adjacent. We don't know the adjacent. So if we say which trig value do we need to use? Think about it. So we have, we do know SOHCAHTOA, trig rules, and tan is opposite on hypotenuse is sine. Adjacent hypotenuse is cos, and opposite on adjacent is TOA. Okay, so we end up with tan 3.8 degrees. Let's do this in meters, is equal to 1500 on on distance glide. Okay, so we're using tan. So therefore, distance glide is equal to 1500 divided by tan 3.8 degrees. So we get out our calculator and we go 1500 divided by, I'm going to go open bracket, tan 3.8 degrees, and go equals, okay? And we end up with 22,583, okay? Now, our book gave us a distance of, 22.5 kilometers, okay? So yes, we end up with DG in meters of 22,583, and we divide by 1,000, so distance glide is equal to 22.5, it's actually 0.6 kilometers, okay? So, will he be able to glide? Well, he can actually glide past the airport. So the answer is, yes, he can glide to airport, okay? Because he's only going to go 16 kilometres. In fact, he's probably going to have to lower his angle of descent to get himself on the correct glide path. Maybe throw out some flaps. I don't know if you'd use a speed brake on an approach with no engines. You'd probably err on the side of caution. But that's up to the pilot. All we know is that, yes, he can make it. So that's example 3.2. And that's an example, once again, of how to manipulate this equation. Theta is equal to thrust minus drag over lift for small angles. Hope that helps explain it.